The Parramatta River in New South Wales rises as a tiny stream some 20 miles west of Sydney. As it develops, it passes through many secluded parklands, providing playgrounds for children. The river was first navigated as far as Parramatta by Governor Phillip shortly after landing with the first fleet in 1788. He was responsible for siting the city of Parramatta. The river reaches the great metropolis of Sydney as it flows into the harbour, which discharges into the Pacific Ocean through Sydney Heads. Only one major high-level bridge spanned these waterways prior to 1960. The ever-increasing volume of traffic caused the other most important bridge at Gladesville to become obsolete. In the latter part of the 19th century, this bridge was an engineer's pride. The two narrow lanes became inadequate for modern needs. A new and wider bridge was called for. Colliers passed through the swing span and road traffic came to a standstill. This created traffic congestion, particularly in peak hours. In preparation for the building of a new bridge, excavations were made on both riverbanks. Coffer dams to keep back the river water were built on the shoreline on either side of the river to permit excavation for the giant thrust blocks which would carry the concrete arch. Concrete was poured for the arch thrust blocks. Thousands of yards of concrete discharged from hoppers into the prepared excavations. The arch thrust blocks take shape. The approach spans to the main arch will be carried on long, slender concrete piers. The bases for these piers are formed up for the concreting, steel reinforcement added, and more concrete placed. The pier columns are vertically pre-stressed with high tensile steel bars. When the concrete in the piers is strong enough, the vertical bars are stressed. The required stressing load is applied with a jack and the stressing nut tightened down. With the pier columns completed, a cage of steel reinforcement is fabricated on the ground and lifted into position to form the headstock. In the meantime, on the southern shore, a casting yard has been set up for the manufacture of the pre-stressed concrete deck beams. Stressing jacks are applied at both ends of the beam, and the necessary extension of the pre-stressing cable is checked and recorded. The finished deck beams will be placed in position using a steel truss, which must be first launched from the abutment to the headstock of the first pier. The deck beam is moved into position along the launching truss until the forward end reaches the headstock. The truss carrying the beam is winched sideways until the beam is in the correct position. The beam is then lowered, one end on the abutment and the other on the pier headstock. Meanwhile, foundations for false work to carry the arch are being prepared. On the bank, tubular steel columns are cut and welded. These will be placed on tubular steel piles, which are driven to the rock below the riverbed, and will form a temporary steel structure known as false work, which will carry each of the 4 ribs of the arch until it can support itself. A diver checks the condition of the steel tube piles. Tugs tow the welded steel columns fabricated downriver into position for erection on the pile caps. Titan, Sydney's largest floating crane, lifts a column from the water and places it gently on the pile caps, where it is secured to previously set bolts. A total of 19 pairs of columns will be placed in position for carrying the steel spans on which the ribs of the concrete arch will be erected. With the columns in position, the steel girder spans, which have been assembled on shore, are now placed. The false work girders join up and are bolted together. Whilst the bridge is being built, a shipping channel must be provided by leaving a 200-foot opening in the falsework columns at the deepest part of the river. 2 steel trusses to span the shipping channel are lifted into position by the Titan. Ballast tanks of water on the end of a truss are used for balancing and close adjustment of the truss position. The second truss is raised into position. Engineers look forward to the next stage of construction now that the temporary steel structure is ready to take the first of the 4 ribs of the concrete span. Some distance downstream, a site has been developed for casting the hollow concrete box units and diaphragms which will form the arch. Concrete is distributed by monorail. Finished boxes are cured with water for several days. Soundness of the finished units is checked with an ultrasonic testing device which measures the time taken for very high frequency sound waves to pass through the concrete. The stockpile of finished box units soon builds up. The diaphragms, or stiffening blocks, which are only 2 feet thick, are reinforced with steel bars and incorporate ducts through which steel cables will run the full width of the arch, tying the 4 ribs together. Diaphragms are cast on prepared beds in the same manner as the boxes. Some completed diaphragms. A laboratory fitted with equipment to measure and test the strength, durability, and other properties of concrete was established. Special gear at the casting yard is employed to lift the boxes onto barges for transport to the bridge site. Back at the bridge, all is in readiness to receive the first of the box units brought from the casting yard by barge. The lifting winch first turns the block upright for placing on the falsework. It is placed on a trolley for movement across to the falsework. And onto another trolley, which will transport it down the slope of the arch to its final position. At intervals, a diaphragm is placed between the box units. Diaphragms, unlike the hollow box units, are solid components with an opening allowing access through the completed arch ribs. Spaced at 50-foot intervals, they serve to tie the 4 ribs together and support the slender pre-stressed columns which will carry the roadway. As the first diaphragm moves slowly down the falsework, an artist captures progress on the world's longest concrete arch. Using modern survey instruments, units are located with extreme accuracy. And so the first great rib progresses. The final box is raised to complete the first of the 4 ribs. This is the 127th unit. So far, some 6,000 tons of concrete have been accurately placed on the steel falsework. After erection of the concrete boxes and diaphragms, the 3-inch spaces between them are filled with concrete. Seen through the opening in one of the diaphragms, inside the first huge rib, the side joints are filled and the rib becomes a continuous concrete span. A model demonstrates the raising of the concrete rib by 3 banks of hydraulic jacks in jacking diaphragms. Pressure forces the concrete units onto the riverbank foundations, and the rib lifts from the falsework. In a control room, on top of the arch, French, English, and Australian engineers work together to carry out the jacking operations. Delicate electronic instruments record movements of the arch during jacking, while the effect of the expanding jacks is closely examined. Conveyors keep a continuous check while jacking proceeds. All measurements are relayed to the control room. The arch has finally risen clear of the falsework. Cement grout is prepared and pumped into the jacks one by one, replacing the hydraulic fluid. When hardened, it keeps the rib permanently in the extended position. This is one of the jacks used in the diaphragms. It is expanded by filling with oil under pressure. Cross-sections of an unexpanded jack, an expanded jack, and an expanded jack filled with cement grout which has replaced the oil. These jacks were developed by a noted French engineer, M. Freycinet, who pioneered the use of pre-stressed concrete. This sketch illustrates the manner in which the jacks are placed around the diaphragm. The model shows how the falsework is moved sideways in preparation for erection of the second rib. Closely synchronized hydraulic jacks on each pier slowly draw the falsework along greased rails. Steelwork weighing hundreds of tons and over 130 feet high is moved as a single unit, inch by inch, to the second rib position. This operation will be repeated later for erection of the third and fourth ribs. Progress becomes apparent as seen from the air. As work on the arch moves forward, a headstock on the shore piers to support the deck beams is constructed. A stockpile of deck beams awaits completion of the arch. Placing of components continues in the fourth arch rib. The casting yard is empty as the last block awaits transport to the bridge. There are 432 box units and 76 diaphragms, each weighing about 50 tons, in the four ribs of the arch. The last of the 508 units is being lifted into position just 1 year after the first box was placed on the first rib. Here, the last box unit slides into position to achieve a triumph of bridge design and construction. Gaps between the diaphragms are filled in with concrete to form a single unit across the four ribs. To give the arch greater stability, steel cables are placed in spaces between the foreribs and stretched. Hydraulic jacks tighten steel cables threaded through the ducts in the diaphragms, providing lateral strength and converting the foreribs into a single arch. The world's longest concrete arch, with a clear span of 1,000 feet, now stands erect, and the falsework, which served temporarily to hold up each rib, is ready for removal. Steel girders on which the concrete boxes rested are lowered. The floating crane hoists a pier column to the arch and sets it in position. High-tensile steel rods anchored in the arch are ready to receive and secure the columns. A temporary brace assists the column to stand erect until the top is tied into the deck of the bridge. A second column has been placed in position, and the two will be connected at the top by a headstock. The floating crane lifts the headstock from the barge. The headstock is fastened to the columns with high-tensile steel rods. A 65-ton beam is then winched along under the truss for seating in position. While construction of the deck progresses, removal of the steel falsework continues. At the top of the arch, concrete slabs weighing about 1.5 tons each are laid in place to support the deck of the bridge each side of the crown of the arch, 150 feet above high water level. Meanwhile, road-making plant is in action, landscaping the approach surrounds. At the northern end, approach roads take shape. Meanwhile, the falsework columns are lowered and floated away. On the arch, the last of the headstocks is maneuvered into position. Near the crown of the arch, the deck of the bridge is supported on low walls in cell-like formation. Elsewhere, the deck is formed by beams and concrete cast in place between them. Deck beams cast on the northern approach for the southern side are lowered by crane to a barge for the river crossing. provide for a footway on each side of the bridge, the deck is extended laterally. Construction of the bridge is nearly completed. The last of the 143 beams which form the deck system of the bridge is maneuvered into position to form a continuous base for the 6-lane road. The falsework has now been removed, and the arch is seen in graceful perspective. On deck, work proceeds on several fronts. A concrete base is poured for the outer protective barrier. Interlocking steel sections are provided, allowing for expansion and contraction with temperature. Outer protective barriers are fitted. Concrete footway slabs are trimmed. Barrier railings separate road and footways. A median strip separates traffic lanes, 3 in each direction. Footway slabs are lifted into position. Earth is graded on the approach surrounds. Lawns are laid and rolled. Finally, the deck of the bridge and the roads in approach are sprayed with bitumen, and the asphalt running course is laid. The road and bridge builders have completed their work, and the new Gladesville Bridge is ready for the opening ceremony, performed by Her Royal Highness Princess Marina, Duchess of Kent. As traffic flows smoothly and rapidly over the new Gladesville Bridge in newly found freedom, we come to the end of the story of the construction of the longest concrete arch, in fact the longest concrete span in the world. It is also the story of the beginning of Sydney's Northwestern Expressway, which will stretch ultimately from the city to join up with the expressway being built northwards towards Newcastle.